Welcome to the late shift. It's quiet, the terminal's glowing, and you're staring down a massive machine learning problem.
The classic 2 a.m. roadblock.
Exactly. What if I told you that to completely alter the mind of a 70 billion parameter AI, to turn it from like a generic chatbot into a master software engineer, you only need to change less than 1% of its brain?
It sounds like a gimmick, but it's actually just highly efficient engineering.
Right. So today we are doing a deep dive into the toolkit of lightweight fine-tuning. Our mission here is to figure out how to update a massive model's behavior without the catastrophic computational overhead.
Which is huge for developers.
Totally. And for our sources today, we are pulling directly from a stack of core machine learning research papers and architectural documentation on parameter-efficient fine-tuning.
Yeah, we really want to map out the practical mechanics of this stuff, because to understand why this toolkit is so critical, we kind of have to look at what traditional fine-tuning actually does under the hood.
Right, the old brute force method.
Yeah. For a long time, the standard practice was to load a model, feed it new training data, and update all of its internal parameters.
Which is fine if your model is tiny, but
if you have 100 billion weights, you are calculating gradients and storing optimizer states for every single one of them. The memory footprint required just to process those updates is, well, it's easily triple or quadruple the size of the model itself.
oh wow, so you need an insane amount of hardware.
Exactly. It is computationally ruinous for a single developer or, a small team.
So we need precision engineering instead of a sledgehammer. And the approaches we are mapping out today from the source docs allow developers to target just a tiny fraction of this system.
Yeah, a surgical strike on the architecture.
I love that. So I want to start with the most physical, structural approach in the toolkit, which is adapters.
Ah, yes! The hardware hack.
Right. If we treat the neural network like a massive, complex pipeline, adapters are where we actually start inserting new plumbing.
That physical pipeline analogy works really well, actually. With adapter layers, we are inserting small, discrete modules directly between the existing frozen transformer layers of the model.
And by frozen, we mean we absolutely do not touch them during training.
Right. The massive pre-trained layers, the ones that contain all the fundamental understanding of language and logic, they remain completely locked. We only train these tiny new inserts.
Okay, let's unpack the mechanics of that insert, because the source material describes a bottleneck structure.
Yes, a very specific three-step architecture.
Right, it's down project, activate, and up project. And, for the back-end engineers listening, this sounds remarkably like a data compression and decompression microservice.
Oh, that's a brilliant way to frame it.
Yeah, like we take a massive payload, compress it down to save bandwidth, run some transformation on it, and then blow it back up before passing it to the next service.
That is the exact mathematical mechanism happening here. A standard transformer layer operates in a massive high-dimensional space.
We're talking thousands of dimensions, right?
Yeah, thousands of dimensions of vector data flowing through at any given moment. So if you insert a new layer of that identical size, you instantly introduce a massive computational bottleneck, but in the worst way. Your processing time just spikes.
Right, you ruin your throughput.
Exactly. So the adapter takes that high-dimensional representation and down projects it. It multiplies the data by a matrix that forces it into a much smaller dimension.
But wait, hold on. Let me push back on this for a second. If we are bottlenecking the data, that drastically, squeezing thousands of dimensions down to almost nothing, how are we not losing all the critical information?
That's the intuitive fear.
Yeah. If you compress a high-res image too much, it just turns into pixelated garbage. Why doesn't that happen to the model's logic?
It's because of what the adapter is fundamentally trying to achieve. When you fine-tune an AI to, say, summarize legal contracts, you are not teaching it the English language from scratch.
Right, it already knows English.
Exactly. You aren't teaching it basic syntax or what a sentence is. All of that foundational high-dimensional knowledge is already baked into those frozen layers we talked about.
Okay, I see where you're going.
The adapter only needs to capture the tiny, specific shifts in logic required for your new task.
So it's capturing the delta. Just the difference between general English and legal English.
Yes, precisely. The bottleneck forces the adapter to learn only the most highly condensed essential features of that specific task. It strips away all the general noise and focuses entirely on the delta.
That is so smart.
And once it applies that tiny behavioral shift in the low-dimensional space, which is the activate step you mentioned, passing it through a nonlinear function, it then projects the data.
It moves it back up?
Right. It multiplies it back out to the original high-dimensional space so it perfectly matches what the next frozen transformer layer expects as an input.
It's like the base model is this massive cargo ship, and the adapter is just the rudder. You don't need a massive steering mechanism to turn a huge ship. You just need precise leverage.
That's a great analogy.
And the math from the research really backs this up. By doing this squeeze and expand maneuver, these adapters add less than 1% of the total parameters to the model.
Which is mind-blowing.
It really is. And they do that while achieving a quality that is nearly identical to a full system fine-tuning run.
Yeah, your compute costs drop off a cliff, and you are only saving the tiny adapter weights on your hard drive.
Not a whole new copy of a 70 billion parameter behemoth.
Exactly. It completely changes the economics of deployment for engineers.
Okay, so adapters are great if you don't mind tinkering with the model's physical plumbing. But what if the model is a black box? Or what if your deployment environment means you absolutely cannot alter the physical architecture?
Right. What if you are strictly locked out of the hardware side?
Exactly. How do you steer the model then?
Well, this is where we shift from a hardware modification to something much more abstract. We move to prefix and prompt tuning.
Ah, okay. The Jedi mind trick approach.
I like that. Yeah, if adapters modify the internal pathways, these tuning methods modify what the model is paying attention to without touching the physical architecture at all.
So no inserting layers.
None. Let's examine prefix tuning first. The mechanism here involves prepending learned virtual tokens to the key value pairs at every single transformer layer.
Wait, let's unpack virtual tokens, because normally a token is just a piece of a word.
Right, like a syllable.
Yeah. If I type the word initialize, the model converts that into a token, which translates into a vector, basically a string of numbers it can do math on.
Yeah.
But what makes a token virtual?
So a virtual token doesn't correspond to any actual word in the human dictionary.
Okay.
It doesn't mean initialize or the or apple. It is purely a continuous vector in the model's embedding space.
The mathematical space where the model maps the relationships between concepts.
Exactly. During the training phase, we keep the entire model frozen. But instead of updating the model's weights, we use gradient descent to optimize the numbers inside these virtual tokens.
Wait, really? We're just optimizing the input?
Yes. We are mathematically searching for the exact sequence of arbitrary numbers that, when fed into the model, forces it to adopt the behavior we want.
Oh, that is fascinating. So instead of hard-coding changes into the system architecture like we did with the adapter, this is like injecting environment variables at runtime.
Yes.
We are slipping these invisible, highly optimized instructions right alongside the actual user input.
And we are slipping them in at a very specific location. Prefix tuning injects these virtual tokens into the key value pairs at every single layer.
Okay, why the key value pairs?
Well, inside a transformer's attention mechanism, the keys and values dictate how the model reads information. They determine which parts of a prompt the model should focus on.
Ah, so it's all about attention.
Exactly. By injecting your optimized virtual tokens into that attention mechanism across the entire depth of the network, you are hijacking its attention. You are constantly reminding it of its new task at every single stage of processing.
It's like setting up invisible detour signs inside the model's logic flow. But, I know there is a simpler, more lightweight variant of this called prompt tuning.
Yeah, the lightweight cousin.
Right. How does that differ from the prefix approach?
Prompt tuning restricts this injection to the very first layer. You only learn and prepend these continuous virtual embeddings at the input layer, alongside the user's actual text prompt.
So you don't touch the key value pairs deep inside the network?
Nope, just the front door.
Okay. But if prompt tuning only happens at the input layer, why would anyone use the more complex prefix tuning at every layer? I mean, if I'm trying to optimize for efficiency, shouldn't I just whisper my environment variables at the start and let the model do the rest?
You'd think so, but think of a deep neural network like a massive, complex game of telephone.
Oh, I see where this is going.
Yeah. In prompt tuning, you are whispering your instructions to the very first person in the line. As that information gets processed, abstracted, and passed through dozens of layers, the influence of those initial virtual tokens begins to degrade.
It gets diluted.
Heavily diluted by the sheer volume of computation happening across all those frozen weights.
So by layer 80, the model is so deep into processing the user's input that it might have completely lost the thread of the subtle prompt you whispered at layer 1.
Exactly. Prefix tuning solves that degradation. You are whispering those instructions to every single node in the telephone line.
You're just enforcing it everywhere.
Right. You enforce the behavioral constraint at every layer, ensuring the model stays strictly on task. But, you pay for that control.
There's always a trade-off.
Always. Prefix tuning requires more memory during training and inference because you have to store and calculate those virtual tokens across the entire depth of the model, whereas prompt tuning only deals with them once.
That makes the trade-off incredibly clear. But the technology hasn't stood still, has it?
Yeah.
I mean, the architecture of the most popular models today, the ones developers are actually building applications on top of, has evolved.
Oh, absolutely.
And specifically, the source material notes that the shift to massive autoregressive models changed the calculus on these tuning methods.
It really did. See, the early days of this research were often focused on bidirectional models, which analyze an entire sequence of text all at once.
Like BERT.
Yes, like BERT. But today, the dominant paradigm is autoregressive text generation.
The GPT style.
Exactly. These are models that generate output strictly left to right, one token at a time, constantly predicting the next word based on everything that came before it.
So why does that left-to-right generation cause problems for something like basic prompt tuning?
Because of context saturation. In an autoregressive model, as it generates token after token, say you ask it to write a 500-line Python script, the context window fills up with its own generated output.
Right. It has to read what it just wrote.
Yeah, and as the sequence grows longer and longer, the attention mechanism naturally starts focusing heavily on the recently generated code to figure out what comes next. The mathematical weight of that initial prompt you injected at the very beginning becomes incredibly diluted.
Ah, so the model drifts.
It drifts badly.
It basically gets distracted by its own output.
Yes. So, to combat this, researchers developed p-tuning. This extended the concept of continuous prompt learning specifically for autoregressive architectures.
Okay, how did p-tuning change the formula?
Instead of just learning flat, static vectors for the virtual tokens, p-tuning introduced a small, specialized network to generate the prompts dynamically.
Hold up, let's unpack that specialized network. I've
Good.
seen it described in the docs as using an LSTM or a multi-layer perceptron.
Yeah, usually an LSTM.
Right. For the front-end developers listening who, spend their days in React and might not build deep learning architectures from scratch, what role is that specific component playing here?
Good question. So, an LSTM is a long short-term memory network. It is fundamentally designed to process sequences of data and remember patterns over time.
Okay, so it handles sequence logic.
Exactly. By using an LSTM to generate the virtual tokens, rather than just treating them as independent, isolated numbers, p-tuning forces the virtual tokens to have a sequential, logical relationship to one another.
Oh, interesting.
Yeah, it binds the continuous prompt together, which provides much stronger, more coherent guidance for a model that naturally thinks sequentially.
Oh, even that wasn't enough, right?
Yeah.
Because the field almost immediately moved to p-tuning v2.
It moves fast.
It really does.
Yeah.
And I'll admit, looking at the papers, I was a bit lost on the jump to v2. If we already had prefix tuning doing the whole whisper at every layer trick,
Yeah.
what is p-tuning v2 actually bringing to the table for these left-to-right models? Are we just recycling old ideas?
It looks like a loop, but it is actually a progression. Researchers realize that for deep autoregressive models to perform highly complex downstream tasks like, complex reasoning or structured data extraction, optimizing the input layer with an LSTM simply wasn't robust enough.
The left-to-right drift was still too strong.
It was. So p-tuning v2 takes the deep layer-by-layer control mechanism of prefix tuning and optimizes it specifically for the architecture of modern autoregressive models.
Wait, so what happens to the LSTM?
It abandons it.
Mhm.
It drops the complex LSTM prompt generator entirely and goes back to applying independent continuous prompts at every single transformer layer.
So we stripped out the complicated sequence generator and just went back to brute forcing the virtual tokens at every layer.
Pretty much.
Just because depth control matters more than sequential generation for modern LLMs.
Exactly. The tool has to match the machine. An autoregressive model requires persistent, unyielding guidance across its entire depth, otherwise it just wanders off task. P-tuning v2 is the optimization of that persistent guidance.
Wow, okay. So, all right, let's put this into practice. Let's look at the developer's cheat sheet.
Let's do it.
I'm sitting at my terminal, I have an open source model, and I need to start writing code today. We have adapters, prefix tuning, prompt tuning, LoRA, p-tuning. It is, frankly, overwhelming. How do I actually choose the right tool for the job?
Well, engineering is the art of navigating constraints. Your choice is entirely dictated by what you are optimizing for.
Okay, let's say my primary constraint is general purpose efficiency, meaning I need a reliable, widely supported way to fine-tune a model across a huge variety of common tasks without blowing up my compute budget.
In that case, the industry standard is LoRA.
Low-rank adaptation, which, we've covered extensively before, basically injecting low-rank matrices into the attention weights.
Right. It provides massive parameter reduction and is heavily supported by almost every modern machine learning library out there.
But what if my constraints are different? Let's say I'm building an enterprise application. I want one massive centralized base model, but I need it to handle a dozen completely different specialized tasks for different users.
You need multitask composability.
Yes, exactly.
Then you reach for adapters.
Okay, but why are adapters so much better at playing nice with multiple tasks than the virtual token methods? I mean, if I have different prompts for different tasks, can't I just swap the environment variables?
You can, but think about the physical reality of the deployment. Adapters are discrete, isolated bottleneck modules physically inserted into the pipeline. They're totally separate from the base model's logic.
Right, they're actual hardware blocks. Well, software hardware.
Exactly. So if you train one adapter for writing SQL queries and a completely separate adapter for translating French, you have two highly modular pieces of code.
Okay, I see.
In a production environment, you load your massive 70 billion parameter base model into your GPU's VRAM just once. Then, as user requests come in, you can dynamically hot swap those tiny adapter modules in and out in milliseconds.
Oh, that is so cool. It's like swapping game cartridges in a console while the console is still running.
That's a perfect way to put it. It is incredibly clean from a systems architecture perspective.
And the virtual tokens aren't as clean.
Not for this. Prefix tuning involves continuously feeding highly entangled virtual tokens deep into the attention mechanism at every single layer.
Yeah, that sounds messy to manage.
It is. Managing, storing, and rapidly composing multiple sets of deep virtual tokens across a clustered production environment introduces much more operational complexity than simply routing network traffic through a distinct adapter bottleneck.
That makes perfect sense. Structural modules are inherently easier to swap than deep behavioral instructions.
Exactly.
But what about our third constraint? What if my goal is to steer the model with the absolute bare minimum of additional memory overhead? Like, I need minimal parameters.
That is where prefix and prompt tuning become the ultimate choice.
Let's dig into the why there. Why do the virtual token methods require so few parameters compared to something like an adapter?
Because of what you are actually saving to disk. With an adapter, you are training and storing two actual neural network layers.
The down projection layer and the up projection layer.
Right. Even though they are a bottleneck, they still contain a matrix of weights. With prefix or prompt tuning, you aren't storing neural network layers at all.
What are you storing then?
You are only storing a tiny matrix of continuous vectors, the virtual tokens themselves.
So you are literally just saving the hyper-optimized environment variables.
Yes. The memory footprint required to store a few hundred optimized vector embeddings is orders of magnitude smaller than even the smallest neural network layer.
That's incredible.
It really is. If you are operating in an environment with extreme memory limitations or, you need to transmit the fine-tuned instructions over a network with very low latency, prompt tuning offers a microscopic footprint that physical architectures just can't match.
Stepping back and looking at the landscape we've mapped out today, it's wild. We started with the seemingly impossible problem of updating a massive AI without infinite compute.
And found a whole toolkit to solve it.
Yeah. We explored the hardware hack, inserting tiny bottleneck modules that squeeze and expand data to capture the delta of a new task, adding less than 1% of parameters while achieving incredible quality.
The adapter method.
Right. Then we shifted to the abstract approach, prefix and prompt tuning, where we leave the physical architecture alone, and instead inject mathematically optimized virtual tokens, either at the input layer or at every layer, to just perfectly steer the model's attention.
Which is basically hijacking the attention mechanism.
Exactly. We saw how those techniques evolved into p-tuning v2, specifically to fight the context dilution in modern left-to-right generating models.
By returning to that unyielding depth control.
Yes. And finally, we built the decision matrix. LoRa's here for general efficiency, adapters for hot swapping tasks in production, and prefix or prompt tuning when your parameter budget is virtually zero. We actually know exactly how to efficiently update a model's behavior without melting our GPUs.
We do, but, that leaves us with the critical next step.
Oh.
The mechanics of steering are useless if you don't know where you are driving. We have the wheel, but how do we format the data so the model actually understands what we want? The source material leads us directly into instruction tuning. It is the crucial bridge between a base model that just statistically predicts the next word and a truly useful assistant that can comprehend and execute complex human directives.
Man, that is going to be a phenomenal deep dive. But before you log off and get back to your terminal, I want to leave you with a final thought about the sheer scale of what we are actually manipulating here.
It's definitely something to chew on.
It really is.
Yeah.
If we can entirely redirect the capabilities of a massive monolithic AI, shifting it from a generic text predictor into a specialized precision tool merely by tweaking less than 1% of its architecture, or by prepending a handful of invisible mathematical tokens. What does that say about the intelligence already resting inside these systems? How much latent, untapped capability is sitting entirely dormant in those frozen weights, just waiting for the exact right key to unlock it?
It really makes you wonder what else is hiding in there.
It does. Thanks for joining us on The Late Shift. See you next time.